So yeah. Oops. Yes. If you could just, I mean, it's my, I will have to over here. Oops.
Okay.
Yeah. Yep. Okay, now it's better. Okay. Can you guys hear me? Hello. Can you hear me, people attending online? Yeah, very okay. Yeah, okay. Awesome. Great. Thanks. Okay, so let's get started. We'll do a review on rings, and then I'll take your questions if you guys wish to ask other questions. What will we start with? Where did we stop last time? Is there any question we didn't do from the first sheet?
We didn't do the last one.
We didn't do the last one. What is the last one? Oh, okay. Write down the units and the zero divisor. Is that okay? Should I do it or it's good? It's good? Should I do it? Yeah. Okay. Write down the units and then the zero divisors. Of at 5 of x modulo x squared. Okay. How many elements do I have here? In this ring, how many elements do I have? How many elements?
25.
25 elements, right? So it's a finite ring, right? What do I know about units and zero divisors in a finite ring? Every non-zero element is either a unit or a zero divisor. So if I find all units, the remaining one are zero divisors, provided they're not zero. Or if I find all zero divisors, the remaining ones are units. That's how we do it. Now, when is so let f of x plus x squared and then 5 of x mod x squared be a unit. Well, or f of x is a unit if and only if what? There exists g of x such that f of x g of x plus x squared is equal to 1 plus x squared. Isn't that right? You can find an element so that when you take the product f of x g of x, it's equal to 1, right? In that ring. Is that right or not? Are we good here? Did I go too fast on this one? Did I go too fast? So one is f of x is a unit, meaning that I can find a g of x, such that f of x plus g of x is equal to 1 plus x squared. Isn't that right or not? This is what it means. This is what it means for f of x plus x squared to be a unit. Means you can find an element. It's of the form g of x plus x squared. So when you take the product, you get 1, which is the multiplicative identity of this ring. Are we good here? Is it clear? Yeah. What does it mean to be a unit? You can find an element b such that a times b is equal to 1. A is a unit if you can find an element b such that a times b is equal to 1. Are we good? Yes or no? Is it clear? Now, what is a times b? This is just f of x, g of x plus x squared. Agree or not? Yeah.
Why does it equal 1 plus x squared? Like,
You're working in this ring, in the quotient ring.
so that's the identity.
That's the identity. Yes,
Okay.
1 plus the identity. Just a second. Perfect. Wait, how's that quotient ring?
Can you voice the yes.
Okay, is that clear or not? Is that clear or not? Is it clear? What's the identity in this ring? What's the one of this ring? It's the cosine 1 plus x squared. Boom, boom. Okay, great. What does it mean? If and only if. What does it mean? If and only if there exists, let's say, k of x, such that f of x, g of x, minus 1 is equal k of x, x squared. K of x is an f5, g of x is an f5 of x. K of x is an f5. Are we good here or not? F of x, g of x minus 1 will belong to x squared, to the ideal generated by x squared. What does it mean to belong to the ideal generated by x squared? It means you can write it as k of x times x squared. Right or no? Is it clear or not? What does it mean that f of x plus g of x is equal 1 plus x squared? This means that f of x, g of x minus 1 belongs to the ideal generated by x squared, right? Subtract 1 from both sides. You get that f of x, g of x minus 1 belongs to the ideal generated by x squared. Yes or no? X plus I is equal to y plus I if and only if x minus y belongs to I. Subgroups? Yeah. If I replace here by I, it's clear. It's more clear if I replace by I. You agree that if f of x, g of x plus x squared is equal 1 plus x squared, it means that the difference belongs to x squared, right? To the ideal generated by x squared. Yes or no? X plus I is equal to y plus I. If and only if x minus y belongs to I. Right? X plus I is equal to y, well, the x here. T plus I, well, t plus I is equal to 1 plus I. It means that t minus 1 belongs to I. What does belongs to I mean? It means I can write it as x squared times something, right? Well, that happens if and only if what? The GCD, bring the x squared to one side, bring the x squared, and bring the x squared to the other side. That's good, huh? It's nice. Is it clear or not? Is it clear? Just if you bring the kx x squared to this side and you put the 1 to the other side, this implies that the GCD of f of x squared is 1. And you can go upstairs as well. If the GCD of f of x squared is 1, then you can find the k of x such that. So far so good? Same proof for integers. Same proof for integers. One is a invertible mod n if and only if GCD of a n is 1. Same proof. One is f of x invertible in this quotient ring if and only if f of x mod x squared or f of x is coprime to x squared. That's it. So when is f of x not a unit? If and only if GCD is different than 1. So let f of x not belonging to x squared, basically so that f of x plus x squared is different than 0. F of x plus x squared is not a unit if and only if GCD f of x squared is different than 1. Agree? It's a unit if and only if the GCD is 1. It's not a unit if and only if the GCD is, well, I mean, you may remove that. I just want to say it's a zero divisor. Okay, that's it. Is not a unit if and only if GCD of x f x squared different than 1. Now, what can you assume the degree of f of x? The degree of f of x, what can you assume it to be? 1 or at most 1, right? We can assume. Wait a second. Can you assume it? No. That's we can assume. Yeah, we can assume that f of x has degree that's really equal to 1. Why is that? Because any cosec of x squared can be represented uniquely by a degree 1 polynomial plus x squared, right? You just take the remainder of f of x by x squared, right? So, what are the possibilities of GCD of f of x and x squared? Has degree at most 1, is monic, and divides x squared. So what is the GCD? If you have f of x of degree lesser or equal to 1, the GCD of f of x and x squared is monic and divides x squared. What is it? X, right? Hence, is 1 or x. So if the GCD is a unit, if and only if the GCD is f of x plus I is a unit, if and only if this GCD is 1. And it's a zero divisor if and only if the GCD is x. And not 0. F of x is not 0. You see that or not? You guys see this? Same thing for mod n. Yes.
How do you know it's monic?
Definition of the GCD. We assume the GCD is monic.
Okay.
And yeah.
Right.
Okay, let's see if people have questions online. Oh, you can't see well. Let's see. Okay. Oops, sorry if you can hear that. If you can move just a bit. Oops. Now it's better? Now you see my head, but is it better now? No problem. Okay. Great. Thanks. If f of x plus I plus x squared is non-zero plus x squared, f of x is a zero divisor, is not a unit, if and only if f of x plus x squared is not a unit, if and only if f of x plus x squared is not is a zero divisor, right? Because it's a finite ring. Since f5 of x mod x squared has 25 elements, finite commutative ring. Oops. If and only if what is the GCD of these? What would the GCD of f of x and x squared be if it's a zero divisor? Could it be 1? It could be x, and if and only if GCD of f of x and x squared is x, if and only if what? F of x, since I assume that f of x has degree 1, what are the possibilities? It's x, 2x, 3x, 4x. Right? So what are the zero divisors? It's the classes of, or the cosets of x, 2x, 3x, 4x, and the units is everything else. Okay? To convince yourself that you're a zero divisor, multiply 2x by x. What do you get? 2x squared. Is it 0 in this ring? Yep. Take x plus 1 and multiply it by what? Multiply it, take x plus 1 and multiply it. Let's see what you multiply it by. Take x plus 1 and multiply it by 4x plus 1. What do you get? Take the class of that. So you get 4x squared plus 5x plus 1, right? What is this? What is x squared in this ring? In this ring, what is x squared? 0. What is 5x? What is 1? Okay. So these are all the units. So these are all the zero divisors. The units is the remaining one. So units, you can write them in this way. They're just of the form ax plus b plus x squared, where b is non-zero, and zero divisors, they're of the form ax, where a is none. Okay? This would also a nice question on final. On the final, this would be a nice question. Find the units and zero divisors. Write down the inverse of x plus 1, for example, plus x squared. These are a nice question. I mean, we've done something like that before, right? We've written the inverse of a number. Yeah. Okay, great. Now, how many units do I have here? How many zero divisors do you have? 4. How many units do you have then? 20. 20 units. What's a good question here? What's a good question? Figure out what is the group of units isomorphic. What group is the group of units isomorphic to? It's a group of order 20. So you'll have to see what is the group of unit isomorphic to. Is it Z20? Is it Z10 cross Z2? Is it Z2 cross Z2 cross Z5? That's a nice question also. Okay, because the units form a group, right? They form an abelian group. What group is it isomorphic? So these are nice questions. You know, like it's a good question. First of all, the first one would be calculation on rings. The second one might involve some group theory, right? We've done some of these, right? We've done some of these, no? Yeah. So this is, for example, a good question. So what group is the group of units isomorphic to? I can tell you. Don't justify your answer. You just tell me what it is. Okay, that's a nice question. So it's a group of order 20. It's an abelian group of order 20. So you can try to figure out what by looking at the order of elements, for example. See what you get. Okay, great. So the first cheat is done, right? The first cheat is done. Okay. The first ring sheet is done. No?
Oh.
Yeah. Okay, but that's a nice question. Think about it. You agree that you have 20 units, right? And it's an abelian group of order 20.
Can you explain that? Wow, I do know 20.
There are 20 units. So just the set of ax plus b, such that b is non-zero. Okay, so you have 5 choices for a and 4 choices for b. So how many units do you have? 20. So it's isomorphic to a group, an abelian group of order 20. Could be Z20, Z10 cross Z2, Z2 cross Z2 cross Z5. I think that's it. Yeah, I think that's it. Okay. No, Z10. So no, it could be Z20. Yeah. or Z10 cross Z2. Z5 cross Z4 is Z20 by Chinese remainder theorem. And then I think that's it, right? You can break that into Z2 cross Z5. Pardon me. So it could be Z2, yeah,
So could it only be one of those?
yeah. Ah, you'd have to eliminate. You'd have to look at the order of elements. You find the order of this element, for example, how many elements? Do you have an element of order 10? Do you have an element of order 20? Yes.
What if we couldn't figure out the group of units?
What if you?
Like, what if that was the first part, like to find the units, but then we couldn't figure that out?
Yeah, no, I'll break it out into parts.
But then if we don't have the first part, we can't. do the second.
No, I'll ask you, show that there are 20 units. Okay.
And then could the next question be, how many group homomorphisms are there from
The group of units to this? No. I'll just ask you to identify the group of units. And I'll tell you, I might tell you don't justify it. Just to check. Okay, now I think it's this one though. I think it's this one, but this is weird. I didn't try that. I didn't try it. But I think it's this one because I highly doubt it's cyclic. I highly doubt it's cyclic. You have an element of order 20, so I highly doubt it's cyclic. I mean, it could be, but I didn't try it. But that could be a question. Okay. I mean, you know, I mean, you can do it many ways. So if you find two elements of order 2, for example, you know it's not cyclic because a cyclic group has only one element of order 2. If it has an element of order 2, it has only one element of order 2. Z20 has only an element of order 2. So you can find how many elements of order 2 this has. I mean, let's write it down. So ax plus b squared is equal to 1. So you have ax squared. So a plus bx plus, what is that? So ax, so it's a squared. It's 2a plus bx plus b squared is equal to 1. So b squared is equal to 1. What do you get? So you need a plus b is equal to 0. Right? And b squared is equal to 1. You have two units. You have two elements of order 2. No. Oh, wait a minute. You have exactly one element of order 2. Right? So if b is equal to 1, so wait a second. No. No, there's something wrong here. A squared x squared plus 2ab. Oh man. 2abx, right? 2abx plus b squared, right? So ab is 1 and b squared is 1. Right? So b is equal to 1 or b is equal to minus 1. What is the x squared? The x squared goes to 0. But this is weird. There's something wrong in here. 2ab is equal to 0. Okay. So you must have a is equal to 0 or b is equal to 0. So you have only one element of order 2. So I think it's Z20. Yeah. It's Z20, I think, yeah. But yeah. But I mean, yeah. So you can find an element of order 20. You see, some things like that might not be easy to guess. Yes.
Will this always hold, like, it's not a zero divisor if GCD is X, or does it depend on the specific polynomial?
Depends on X squared. So if the GCD with the thing you're modeling out by is 1, it's always a unit. That's it. Yeah. Okay. So that's something, huh? I didn't know that. Because you have only one element of order 2. And if you take Z2 cross Z2 cross Z5, yeah, if you take Z2 cross Z2 cross Z5, you have more than one element of order 2. And here you have only one element of order 2. So I think it's Z20, yeah.
So just to make sure, you know you're for x squared. Saying that it has to do because you're x squared.
It's by x squared, exactly. I'm just, yeah. We're modeling out by x squared. Where does x squared go to? 0. 5, you're in F5.
Yeah, exactly.
Exactly.
So is it in
5, if you're in F5, what is 5x? 0. Why are we trying to
but
find
isn't it
1? No, these are equivalence classes. I'm just this is modulo x squared. Modulo x squared. Okay.
So
Okay.
that's why the degree is one.
Exactly. Exactly. Because you're working modulo x squared, so it's a polynomial of degree at most one. Yeah.
Are we trying to find a group that's isomorphic with the elements having order 2?
Where?
If I'm saying let's go to the
Here?
20z, no, we're saying, oh,
No, I'm just trying to find the group of units here.
I mean, before and after.
Yeah.
We're trying to find a group that's isomorphic.
Yeah. So the group of units Z20. How many abelian groups can you find with Z20? It's either like Z2 cross Z2 cross Z5, or Z4 cross Z5, or sorry, or Z20. Now you know if you have Z20, then you have only one subgroup of order 2. That's a property of sigma. For each divisor of 20, you have only one subgroup of order 2, and it's only one element of order 2.
Just an example, be like subgroup of order 3.
If 3 divides the order of the group, yes. Okay, now here you all now, and if you have Z2 cross Z2 cross Z5, you don't have one element of order 2, you have 2 elements of order 2. I don't want to say how many, but you have more than one. You have 0, 1, 0, and 1, 0, 0. So here you have only one element of order 2. So I would say it's Z20. I didn't try it, but I would say it's Z20 just by elimination. Okay. But yeah, I mean, this particular example might be complicated because it's hard to do calculations with 20 elements, right? Especially you have to square them. But this is weird. I didn't expect it to be cyclic. I didn't expect the group of units. Weird. Yeah, you do have 20 units. Yeah, you do have 20 units. So x squared is just 2x plus 1. This is weird. This is weird. Yeah, this is weird. I'll double check. Don't take my word for it. Okay, but if I give you something like that, I'm not going to give you something for that. Okay. Okay. Don't worry about it. It was a question. So no, that you want to have something. No, I'm not going to use it. I mean, I had an example. I had an example like that, but everything was not here. No. It was easy, but I think it was. I want you to justify it. If you justify it, it's going to be a bit longer. So I just removed it. Okay, great. So now let's move on to the second sheet. Okay, so what are the questions that we didn't cover in the second sheet? Why is it? So you're working modulo x squared in F5. So modulo x squared in F5 for x squared, because x squared is 0. In F5 mod x squared, for x squared is 0. 5x, you're working with F5, so the 5 is equal to 0, and you're just left with 1. Noah, yes, that's right. You could just do that. Fg is equal to 0 mod x squared. That's right. Yeah, that's right. Yeah, you could do that. You could find the 0 divisors first and then find the units. Yeah, that's right. Could I just have a look on this? Could I just have a look on the exercises? So let p bigger or equal to 5 be a prime number and fp with the field with p elements. Show that x squared plus x plus 1 is irreducible in fp of x if and only if p is congruent to 2 mod 3. That's also very good. So let p be a prime. X squared plus x plus 1 is irreducible in fp of x if and only if what? P is congruent to 2 mod 3. Great. So, how do we proceed? Did you attempt this or not? Yeah, how do you?
I tried it.
Oh, okay. Yeah, Z5 cross Z4. Well, Z5 cross Z4 is Z20, but I just have to check. Now, you could say that X, if you Z5 cross Z4. So what you're gonna do is this X. If you have X plus 1, and you look at the order of X plus 1. Now I'm tempted to say that X plus 1 will have order 5. I think. Okay, I'm tempted to say that. But then you want me to do the calculation for this one, or let's just do it like that. X plus 1 and X is 2X plus 1. Okay. And then 2X plus 1 squared is 4X squared plus 4X plus 1. It's just 4X plus 1. Okay, so X plus 1 has order 5. Okay, X plus 1 has order 5. Okay, so X plus 1 here has order 5 because 4X plus 1 times X plus 1 is 1. So X plus 1 to the 5 is equal to 1. So X plus 1 has order 5. Now we have to find an element of order 4. Yeah. So what's an element of order 4 and 5? We can take maybe 2, for example, any constant polynomial. X plus 1 and 2. What is 2? What is the order of 2 mod 5? The multiplicative order of 2 mod 5? It's 4, right? 2 has order 4. So now you have a subgroup H1 and a subgroup H2. H1 has order 5, H2 has order 4. The intersection of the two is 1, and they're both normal subgroup. So the group of units is isomorphic to the product of these two. This is cyclic of order 5, this is cyclic of order 4, so it must be Z20. Okay? 2 has, so what is 2 squared? 2 squared is 4. Mod 5 minus 1. Squared again, you get 1. Right? So 2 has order 4 in the group of units. Okay, yeah, so it is Z5 cross Z40, but not because you have 5 choices for A and 4 choices for B. I mean, it's not like because you have 5 choices, you have Z5 here and Z4. I mean, you may be able to write it this way, but this is the correct justification. That X plus 1 has order 5, 2 has order 4, right? And then if you take the intersection of these two, you have 2 subgroups of 2 cyclic subgroups of coprime order. So the intersection of the 2 groups is 1. Now you take the product of these 2 groups, it has size 20. So the group of units is the product of these 2 groups, and it hence isomorphic to H1 cross H2. Okay? Anyways. Great. Okay, let's get back to this. X squared plus X plus 1 is irreducible in FP of X if and only FP is congruent to 2 mod 3. What is the idea here? Plugging in doesn't work, right? Because now what if, note, what is X minus 1 times X squared plus X plus 1? Do you want to expand this? Do you want to have fun expanding? So X cubed plus X squared plus X, right? Minus X squared minus X minus 1. What is this? It's just X cubed minus 1. Wait a minute. That's nice. That's nice, right? So if you have a solution to this, if you have a root of this, A, it must be non-zero, right? And it must satisfy A cubed is equal to 1. So any root of this is an element of order 3 in FP star. Right? Yeah? If a is a root of a squared plus a plus 1, then a is different than 1, right? Because p is bigger or equal to 5. And a will satisfy a cubed minus 1 is equal to 0. So if a is different than 1 and a cubed is equal to 1, then a must have order 3 in fp star. Right? You see that or not? You agree that a, since p is greater or equal to 5, if you plug in 1 here, you will not get 0. P is greater than 5. 1 plus 1 mod p will not be 0 if p is greater than 5. So any root of this is not 1. Right? And it must have order 3. It's not 1, it's not 0. And it must satisfy a cubed equal 1. So it must have order 3. Right? If a squared plus a plus 1 is equal to 0, then what's the order of that? Then a cubed must be equal to 1. Agree or not? If this is 0, then this times this is 0, right? So if this is 0, then a cubed is equal to 1. Agree or not? Yes or no?
Yeah.
Just write this 0 here. If this is 0, then this is equal to 0, then x cubed must be equal to 1. So this says that if you have a root of this polynomial, then it must have order 3 in fp star. By Cauchy's theorem, this happens if and only if 3 divides p minus 1, which happens if and only if p minus 1 is congruent to 0 mod 3, which happens if and only if p is congruent to 1 mod 3. No. Yeah, exactly. So it's reducible if and only if p is congruent to 1 mod 3. So it's irreducible if and only if p is congruent to. See that or not? No, that's yes.
That's the only way there.
Pardon me?
Is that the only way?
That's the way I thought of. Maybe you can do it another way. Maybe you can do it another way, but this is, I think, an easy way of doing it. Okay. Let's do this. X, since x squared plus x plus 1 has degree 2 in fp of x, and p is greater or equal to 5, if a squared plus a plus 1 is equal to 0 in fp, then a is different than 1, right? Because 3 cannot be congruent to 0 mod p if p is greater than 5, right? You see that? If p is greater than 5, 3 cannot be congruent to 0 mod p. And a is different than 0. Right? Because 0 plus 1 is not 0. Right? 0 can a be 0 and satisfy this? No. Okay. If a is correct, then a is different than 1, different than 0. And okay, well that's good. So thanks. A different than 1 and a different than 0, and a squared plus a plus 1 is equal to 0 if and only if a has order 3 in fp star. You see this or no? Because if it satisfies a squared plus a plus 1 and you time it by a minus 1, you will get a cubed minus 1. Are we good? Yeah.
Can you clarify?
Yeah, just to get x cubed minus 1.
Is you
I know it. I know that if you multiply this by x minus 1, you get x cubed minus 1.
But how do we know to get that we want?
Yeah, this is the tough part. Just to know. I mean, you know, I think you've seen the geometric formula, right? 1 plus x squared, what is that? This is just 1 minus x cubed over 1 minus x. Right? You've seen this before? The geometric formula, you did see that. 1 plus q squared in general. No?
Maybe.
You have seen geometric series, no? Or not?
Yeah.
Yeah, this is a geometric series. Kind of. 1 plus x squared. It's 1 minus x cubed divided by 1 minus x. Now we just do it over a field. So you down, yeah. So this is the intuition, yeah.
I just don't quite understand what the whole like note thing is like helping us.
Yeah, because this, you have a root, any root of this polynomial will be an element of order 3.
Yeah, agree.
Okay.
Um,
Now, so a root of this polynomial exists if and only if fp star has an element of order 3. Exactly.
How'd you know that?
If you have a root of this polynomial, then it's not 1, and it has an element of order 3. Right? Now, if you have an element of order 3, then it must satisfy this is equal to 0. Now, since it has order 3, it's not 1. And since you're over a field, this is not 0. But this must be 0. Okay? You guys see this or not? It's a bit tough. This one is a bit tough. This one is a bit tough.
I don't get how we get, once we have a squared plus a plus 1 and equals 0, then that's b, then a is not equal to 1, and a is not equal to 0.
Okay, so, okay, I mean, you know, take this as assumption. A is different than 1, A is different than 0. Erase it. If B is greater than 5, right? In FP.
We give an example of it, some great example.
Yeah, sure. Pick 5, for example. 5 is congruent to 2 mod 3. And what is a squared plus a plus 1? Plug in 1 plus 1 plus 1, you get 3. Is it 0 mod 5?
No.
No, it's not 0 mod 5. Pick any number, and then this polynomial x squared plus x plus 1 will have no roots mod 5. If you plug in all the numbers, it will have no roots. Okay? It's the same thing as if a squared is minus 1, if and only if a has order 4. If b is odd, right? You know this one. You've seen this one, no? We've done this last time. This one you should know, and this one you should know. It's a good idea to know this. Yeah. A is not 0. A is not 0. Why did the order 3 come in? Okay, so let me prove it more properly. Proof. Suppose a squared plus a plus 1 is equal to 0 in NP. Then a is different than 0. Is that clear? Because 0 plus 1 is equal to 1. And a is different than since 1 plus 1 plus 1 is not congruent to 0. Because b is bigger or equal to 5. Agree? Agree or not? Okay. Now, if a squared plus a plus 1 is equal to 0, then a minus 1 times a squared plus a plus 1 is equal to 0, right? This is 0 multiplied by a minus 1. What do you get? 0. Hence a cubed minus 1 is equal to 0. So a cubed is equal to 1. Right? So a has order dividing 3 in FP star, and a is not 1. What's the order of a? A has order dividing 3. Because if a cubed is equal to 1, then the order of a in FP star divides 3. Group theory. If g to the n is equal to the identity, then the order of G divides N.
Oh, okay, because one is the identity.
Exactly, FP star. That's right.
Wait, okay.
Yeah.
So, I mean, so 3 is of the order.
Exactly. So A has order 3 in dividing 3. Dividing 3 in FP star.
Is it dividing 3 or which P divides?
No, it's dividing 3. The order will divide this one. Since A is different than 1, then A has order 3 in FP star. Okay? Let's do the converse. Let's do the other way. Suppose that A has order 3 in FP star. If A has order 3, then A is different than 1. Agree or not? Because 1 has order 1. We agree? And A cubed minus 1 is equal to 0. Right? Because A cubed would be equal to 1. Hence, A is different than 1. And A cubed minus 1 is equal to 0. So far, so good. Yes or no?
Mhm.
Now, let me factor A cubed minus 1. This is A minus 1 times A squared plus A plus 1 is equal to 0. Agree or not? I just factored it.
Mhm.
Now, since FP is a field and this is non-zero, what can I say about this one? Is 0 because FP is a field. Since FP is a field, and A minus 1 is different than 0, then A squared plus A plus 1 is equal to 0. Okay?
Mhm.
And that's the proof. Are we good? Great. So let's prove this now. We can do this now. Suppose A squared plus A plus 1 is, what am I saying? Yeah. Hence, x squared plus x plus 1 is reducible in FP of x. So P is bigger or equal to 5. This should be that. If and only if, since it has degree 2, has a root in FP. It's a degree 2 polynomial. If and only if FP star has an element of order 3. Now, I know one way. I know that if FP star has an element of order 3, then it must be the case that 3 divides P minus 1. Agree or not? If and only if 3 divides the size of FP star, which is P minus 1. Agree or not? Agree? If FP star has an element of order 3, means 3 divides the size of the group. Yes or no? If a finite group G has an element of order 5, what can I say about G is divisible by, the size of G is divisible by 5, right? Yes or no?
Yeah.
Yeah. Now, why is the converse true? Why can I go this way? Why can I go this way? So you know that if FP star has an element of order 3, then 3 must divide FP star. Okay, why is it the case that if 3 divides FP star, then I must have an element of order 3? Cauchy's theorem. 3 is a prime number dividing FP star, the size of FP star. So you must have an element of order 3. Very nice exercise. If and only if P is congruent to 1, 1, 3.
This is part of the 15 you're worried about, right?
If I put this would be part of the 15 I'm worried about. Yeah. Okay. This could be a good question. This is a nice question, but I'll give it to you in steps. This would be 10 marks.
This can be.
A group. I'll give it to you in steps. No, this could be a calculation ring. For example, what I would do is that first I give you f5. I tell you show that x squared plus x plus 1 is irreducible in f5 of x. Okay, you do the calculation in f5, and I ask you to generalize this. In the practice final, you have something like that. I show you, do it for 2 and 3. I give you a polynomial of degree p. Degree p. I told you show it's irreducible if p is 2 and p is 3. So you have to check the roots, right? Because you have degree 2, degree 3. And then I tell you generalize this if p is greater than 5. Here, for example, that's a tough question. Okay. Yeah, but don't worry. Don't worry. If you know how to do these, then you're fine. Okay. Like, I mean, if you don't do these type of questions, then is the a squared equal -1? Is it good or not? Is it? If so, a has order 4, for example. Yeah. So, or t to the 24 minus 1. Find the roots of t to the 24 minus 1 in a field with 25 elements. Yep. These are good. Okay, so you should expect a calculation like that. Now you know. I would give you a hint. I would give you a hint before. I would give you x. Yeah, I'll give you x. Show that x minus 1 times x cubed plus x squared plus x plus 1 is x cubed minus 1. Okay, I'll give you something like that. Okay.
That's like a tiny step. It's like
Yeah, but this is the key step.
Yeah.
This is the key step, right? And I will give you this as a step. Show that fp star has an element of order 3 if and only fp is congruent to 1, 1, 3. I'll give it to you and I'll break it into steps. Okay? Yes. A is non-zero, right? If you have a root here, then a is non-zero. So it belongs to the group of units. Exactly. Okay, are we good here? Yes. Where? Yes, because of this previous here. Because of this one. Yes. Is irreducible if p is congruent to 2, 1, 3. Yes, is reducible here. Right? I have is reducible if and only if p is congruent to 1, 1, 3. No, reducible. Reducible. Reducible if and only if p is congruent to 1, 1, 3. Hence, it's irreducible if and only if p is not congruent to 1, 1, 3. What is it then? If and only if? Hence, x squared plus x plus 1 is irreducible. It's irreducible when fp of x if and only if p is not congruent to 1, 1, 3. Now this happens if and only if p is congruent to 2, 1, 3, since p is bigger than 5. Since p is bigger equal to 5. Right? P cannot be congruent to 0, 1, 3 unless p is 3. Right? A prime number cannot be divisible by 3 unless it's 3. And then you eliminate 3 because p is bigger equal to 5. Nice question. That's a nice question. You could expect something like that. A calculation on rings first, and then a group calculation on the rings, involving the group of units, involving, yeah. Okay, we've done like tens of these, right? We've done. No, I mean, no, I mean that's a group question that has nothing to do with rings. I didn't use anything with rings here, except this one. This property that a field is an integral domain. So really here, there's nothing of polynomials and something irreducible and quotient rings. But this could perfectly go in the first part of the group. Okay, so there is nothing, I'm not using any theory of polynomials. I'm just using this thing. This I could have given you at the start of rings, so that you can find an element such as a squared plus a plus 1, if and only if 3 divides fb star. Okay, so it's not so what is that? 1 plus 1? Where would, no, this would be a difficult question. Yeah, this would be a difficult question. It wouldn't be an easy question. It's irreducible if and only if p is not from the.
Oh.
Okay. Okay, great. Nice questions. People have questions in the chat? No? Okay, great. Yeah. These are nice questions. Okay, let's do the last one. There's one last. So there is one more, no? So, 2 more? Okay, so can I have that? Okay, so please, this order 4 business, this second questions on group business, you should do these. Okay, great. Let's do one more. Could someone read it for me, please? Yeah, could someone read it for me? 4, yes. Yeah.
X squared plus x plus 1 and f2 x mod x squared isomorphic.
Isomorphic. This is also a typical first question. This is a typical question. Okay? This is a typical question. So you don't be shocked if you see something like that. Now you're happy if you see something, right? But I mean, you can expect one part that is easy, one part that is a bit harder, one part that is, or both medium. So like, you know, it will be balanced. You will see. Great. Are these 2 rings isomorphic? Anybody wants to help? Any? So yeah. So raise your hand. Yeah. Okay. How do you justify that? Very good.
Like the other one.
Okay. So what? Okay. Okay. Very good. Why did you say that this one is irreducible if it has no roots? What? No, you check it has no roots.
Yeah.
That's good. But why is it irreducible? This one.
Yeah.
It has no roots. But why is it irreducible? What's the degree? 2, right? You have to specify that.
Okay.
You have to say this has degree 2 and it has no roots, so it is irreducible. Would be the same, but for degree 4, it's not necessarily true that it's irreducible if and only if it has no roots. Okay, very good. Should I write this down or that's good?
Well, what's we have to do anything? It has no roots, therefore it's irreducible.
No, you can still factor something that is irreducible. So take an R of X, for example. You can still factor something that is reducible but have no roots. In real numbers, is this irreducible? No, because you factored it. Right? Does it have a root in the real numbers? No. Okay, but this is an irreducible polynomial. And this is a reducible polynomial with no roots.
Yeah, but take away one side of it, like one part of it, like just x squared plus 1.
Yeah.
That's irreducible because it has no roots.
Because it has degree 2. This theorem works because x squared plus 1 has degree 2.
We'll take a polynomial like degree 4.
Yeah.
But one polynomial, not 2 separate ones.
Multiply them together. You get one polynomial.
Yeah, but no, that's cheating.
Okay.
You can't.
I mean, but this is how you get it.
Okay, fine.
So if you have a polynomial of degree 4, it is not true that it's irreducible if and only if it has no roots.
So it's specified as
You have to specify that this has degree 3. Do you want me to write this down or not?
So you say. It,
So since it has degree 2, it's irreducible in F2. Rx. Do you want me to write this down? Should I write? Yeah. Well, some people want me to write this down, so I'll write it. It's important. It's important. It's important. It's not that it's easy, it's not important. So x squared plus x plus 1 has no roots in the field F2. And 0 squared plus 0 plus 0, 0 plus 1 is 1. And 1 squared plus 1 plus 1 is 1. Right? It's important that the base field is a field, that the thing you're modding, this thing you're starting with is a field. You should specify at least that F2 is a field, okay? In the field F2, since x squared plus x plus 1 has degree 2, this is important, then it's irreducible in F2 of x, then F2 of x mod x squared plus x plus 1 is a field. Well, how many elements does this field have? How many elements does this field have? Any volunteer? How many elements does this field have? Please raise your hands. How many elements? Yeah. 4. Very good. Is a field with 4 elements. The question doesn't ask, but okay. Now F2 of x mod x squared. X squared is not irreducible in F2 of x, since x squared has degree 2. 0 is a root of x squared. Or you can just write it's not reducible because you can factor to 2 degree 1 polynomials, right? Yes.
Since this is a root, then it's reduced.
No, because if you have degree 1, right? So you must specify that it has degree 2. So the degree 1 polynomial has a root, but it's irreducible. Degree greater or equal to 2. If it has a root, then it's not reducible. Then it's reducible. Then it's not irreducible, then it's reducible. Yeah. Over a field, never. Never, because it has a root. Right? Ax plus b is equal to 0, then x is equal to a minus a inverse b. This is a root. Okay? So then 0 is a root of x squared. So what? So F2 of x mod x squared is not a field. Hence, F2 of x mod x squared plus x plus 1 and F2 of x mod x squared are not isomorphic rings. Okay? This is a perfect question as well. This is a perfect question. Are these two quotient rings by polynomials? Yeah, it's a perfect doesn't mean it's gonna be there. Okay, but I'm just saying it's a perfect type of question. The difficulty is perfect. Everything is good. Okay? Yeah.
So still have a 4. Oh,
Both of them has 4 elements. Yeah, exactly. If I were to give you F3 of x mod x squared and F2 of x mod x squared plus x 1, you would say this has 9 and this has 4, so they're not isomorphic. Yeah. Okay. How do we know if it's irreducible when the degree is other than 2? So if the degree is 2 or 3, you just have to plug in and see it has no roots. Now, if the degree is 4 or more, yeah, you have to just check it cannot be factored. Now, I think it goes case by case. I give you an example in the practice final. Okay, something it's a hard one, but it's yeah, but it's 5 points. So you can expect something like that. Like hard questions on 5 points, and it's diluted by easier questions. So I don't put the whole weight of the hard question. Okay, great.
This one's nowhere near as hard as the previous one.
Pardon me?
This one's nowhere near as hard as the previous.
This one here?
Yes,
Is it as hard?
it's nowhere near as hard as
Yeah,
the
no.
previous.
Exactly. It's nowhere near as hard as the x squared plus x plus one thing. But you know, you can expect the final to be balanced. Some parts are very easy, some parts are a bit harder, some parts are medium. So this, how would you rate this? 1 out of 5?
Easy.
Easiest. No, I would count this as medium, for example.
Yeah, like they will be too sweet. Like easiest, like just ask, give that animatable field, whatever.
No, I mean, I would rate this as medium in difficulty, right? Because you have many concepts to do, you have many things to justify. You have to tell me that it has degree 2. It has no roots, so it's irreducible. So this is not a very easy question for me. Yes.
Let's say it was a field, the second, let's say they were both fields.
That's a good question.
For them to be isomorphic, they have to have the same order, correct?
So if that's a good question, that's a bit beyond this course. So if you have two fields with 9 elements, say, then they're isomorphic. Yeah. Any two finite fields of the same size are isomorphic.
Size, order.
So, yeah, order, size. Order is usually reserved for groups, but any two fields of the same size are isomorphic.
So, but say if like one is like a F3 and one is a F2, then they're definitely not.
Not exactly,
Because
because
like,
they don't have the same size. There's no bijection between them. Yeah, but yeah, if you have two fields of the same size, so say you construct. This is why, by the way, when I tell you construct a field with 25 elements, the next question, whatever your field is, for example, what is the characteristic of K? It doesn't depend on the field you constructed. Okay, this is why if you notice the question I did last time, so construct a field with 25 elements, and what's the characteristic of K? And then show that T24 minus 21 has 24 roots. This doesn't depend on what K you constructed. Okay, so this is okay. Great. There is one more. There are two parts to this. Okay, so just F3 plus X mod X squared plus 1 and F3 of X mod X squared plus 2 are they isomorphic? So F3 of X mod X squared plus 1 and F3 of X mod X squared plus 2 are they isomorphic or not? No. Why is that? X squared plus 2 is irreducible. Why is it reducible? 1 is a root. Very good. And why is X squared plus 1 irreducible? Degree 2. X squared plus 1 is irreducible. We're in degree 2. And then has no roots, right? Should I write this down? Or that's good? It's good? Okay, great. So please, this type of question, know how to do this. Okay? Please know how to do this type of question. I give you two quotient rings of the same size and tell you, are these two isomorphic? Most of the times, I mean, one will be a field and one will be not, and one won't be. Okay? Okay, great. Now let's do the last question. Oh, but this one exercise. Show that x cubed plus 11 is irreducible in F13. 13 can actually be 13. Yeah, because the next question. Yeah, 13. It just I didn't put my brackets correctly. Or I forgot to put the brackets in there. Okay. Sorry. X5. 1. Show that x cubed plus 11 is irreducible in F13. 2. Let I be the ideal generated by x cubed plus 11 in R equal F13 of x. Thus there exists A in R mod I such that A squared, what did I write? Is -1. Also perfect questions. All of these are perfect. I mean, everything is perfect. Yeah, but this is a perfect question. One is easy. The first one is easy. I mean, here it's a bit long because you have to check 13 elements. Is it 13 elements? I mean, less. I mean, there's another way of doing it, but that's not good. There's another way of doing it. It's using the xp minus 1 minus 1. You could, anyways, that's not very good. Yeah. You use the first question, it's 2, 3 left. The second question, exercise 1. If you use exercise 1 and that, should be very quick. But anyways, let's not do that. I mean, we have another way of doing it, right? So the first one is easy, right? The first one is easy. And then the second one is a bit harder. Perfect combination of questions. And then if you don't know how to do the first one, you can still do the second one. If you don't get the first one, you can still do the second one. So that's also a perfect, these are perfect questions. Okay, great. Now, one. So how do we show that x cubed plus 11 doesn't have any roots in F13? What do you suggest doing? Yeah. Exactly. So what is A? A, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, and what is A cubed? A cubed 0, 1, 8. 3 cubed is 27. 27 is 1, right? 113, right? 27 is 1. 4 cubed. 4 cubed is 64. 64 is minus 1, right? 64 is minus 1, which is minus 1, which is 12, right? 5 cubed is, what is 5 cubed? 125. 125 is minus 5, right? Minus 5, which is 7.
It's worth having calculated.
Pardon me?
It's worth having calculated.
Well, I mean, you can still do that, right? 6 cubed, what is 6 cubed? 8, you guys have, okay, 8. What is 7 cubed? So 7 and 6, so 7 and, okay, so 7 and 6 is 13, so 7 is minus 6. When you cube it, you get minus 8, right? Minus 8 is 4, right? Minus 8 is 5. Okay, now here you get minus 7, which is 6. 8 cubed is 6, right? 9 cubed, what is 9 cubed? 9 and 4, so this is 1. 9 cubed is 1. So you have 81. 81 mod 13. What is that? This is 3. This is 9 squared. And 9 cubed is just 9 times 3, which is 1. Okay? 10 cubed. What is 10 cubed? 10 is minus 2, so it's minus 8, which is 5. And 11 is, no, what am I saying? 10 is minus 1, right? 10 cubed is minus 3, so it's minus 1, which is 12. 11 is, 11 is minus 8, which is 5, right? And then 12 is minus 1, which is 1. Right? 11 cubed is 11 cubed is 11 cubed is, so 11 cubed, anyways, whatever it is, but it's just 5 mod 13. Okay, 11 cubed 31. Is it 11 cubed? Is it 11 5 mod 13? Check it. Could you check it? Or just on your calculator? 11 cubed mod 13, what is it? I think it should be, because 11 and 2, so 2 cubed is 8, so 11 cubed must be minus 8, which is 5.
Explain your little trick that you do.
So 7 is minus 6, right?
Yeah.
7 is minus 6. So 7 cubed is minus 6 cubed, which is just minus 6 cubed. You look at 6 cubed and you put minus. So 6 cubed is 8. So minus 6. So 7 cubed is minus 6. So 7 cubed is minus 8, which is 5.
What? 7 is minus 6, so 7 cubed is minus 6 cubed.
Yeah. Distribute the cube. You get minus 1 times 6 cubed. Now what is 6 cubed? 6 cubed is 8.
Oh, yeah.
0 minus a. What is minus a? It's 5.
Yeah, fair enough.
Okay? Yeah.
So for the square, it will be like a
For the squares, it will be a mirror. Exactly. For the square, you stop here. You stop at the 6. P minus 1 over 2. Yeah, and you reflect it. Exactly. Okay. So can I find an element whose squared is 11? Whose square is minus 11? Minus 11, what does minus 11 mean? 2. Can I find an element whose square is 2? Whose cube is 2, sorry. So x cubed plus 11. Hence, x cubed plus 11 is equal to x cubed minus 2. Has no roots. In F13. In the field F13. Right? Agree or not? Now, what do I have to say? Since it has degree 3, x cubed plus 11 has degree 3. Then x cubed plus 11 is irreducible in what? In F13. Okay, let's do the second part. Yes.
Can we say that it's two?
Yeah, both of them are 0. Yeah, these are equal. Yeah.
Yesterday you said the table for for
Might not always work, no. So you might get a case that every element is a cubed. So pick let's see. Pick 5. Mod 5, okay? Do it mod 5. 0, 1, 2, 3, 4. Cube everything. You get 0, you get 1. What is 2 cubed mod 5? This is 3. What is 3 cubed mod 5? 3 cubed mod 5 is 4. No, 3 cubed 27.
Oh, yeah.
2, right? And what is 4 cubed mod 5? It's 4. This a polynomial like that won't work. You can still find one of degree 3, which is a few bit more. Interesting. Why does it not work? Yeah, but no. Definitely. But why? Why would this work? Why would this not work? If p minus 1 is not divisible by 3, then every element will be a cubed. If p minus 1 is not divisible by 3, then every element would be a cube. Would be a cube.
Is that general?
Yeah, I think you could do it. You can generalize it, but for prime numbers, the proof is a bit easier. The proof is a bit easier for prime numbers. If p like the p, I mean the three is prime.
Yeah.
I mean, if you use the properties of fp star, that fp star is a cyclic group, it becomes easy. So if you use that fp star is a cyclic group, and p minus 1 is divisible by, anyways, let's not worry about this. Okay, let's not worry about that. But technically, the map x to x cube is not surjective in that case, and if F13 is not surjective. Okay. Anyways, let's not worry about this. Okay? Don't worry about that. Okay, I'll make sure like the simplest polynomials will work. Okay, so
the table should work.
the table should work. Yeah, especially if that's degree 3. For degree 3, I'll make sure the table should work. Yeah. Unless I give you the polynomial. For example, I'll give you the polynomial until you check it's irreducible. Okay, and I won't give you big numbers. I'll try to moderate 7, 5, 3,
Like 20 something.
29. No,
No.
not 29. Okay, so I'll try to be, the numbers will be nice. Okay, great. Now, let's look at the second question. Does there exist an A in R mod I so that A squared is minus 1 plus I? Why are we shaking the heads? Why? We did something similar yesterday. So first of all, what can we say about R mod I? F3 of x modulo x cubed plus 11. What can we say about that? It's a field. Why is a field? x cubed plus 11 is reducible in F13 of x. Very good. So the quotient ring is a field. Great. If you have a squared equal, is 1 equal to minus 1 in this field? No. No. Is 1 equal to minus 1 in this field? No. Now, if you have a squared is equal to minus 1, can a be 0? If a squared is minus 1, can a be 0? No. Now, if a squared is equal to minus 1, a would belong to the multiplicative group of the field, to the group of units, right? Now, what is the group of units of the field? R mod I star. How many elements does it have? 13 cubed minus 1, right? Now, what would the order of A be? What is the order of A in that group, in that multiplicative group? If A squared is minus 1, what is the order of A? 4. We see that? We see that? If A squared is equal to minus 1, what is the order of A? Can A be equal to 1? No. A squared is not 1, but A4 is equal to 1. So A will have order 4. Now, does the multiplicative group of R mod I have an element of order 4? No. Okay, let's do that. Suppose such an A exists. By part A, by part 1, R mod I is a field with how many elements? How many elements does R mod I have? And someone else? Someone else? Please raise your hand. Someone who didn't participate. Yes? 13 to the 3 elements. Okay? Hence, the group of unit of R mod I is a group with how many elements? Is a group with how many elements? The group of units? Yeah. 13 cubed minus 1. We did a question like this yesterday, right? With t squared plus 1 is equal to 0. You remember this? It's the same question. I just phrase it differently. Do you have an element so that a squared is minus 1 plus I? Equivalently, does t squared plus 1 has a root in this field? Okay, suppose A is such that A squared is minus 1 plus I. Then clearly, A is different than 0 plus I, right? Because the square of 0 is what? 0, right? Yes or no? If A squared is minus 1, can A be equal to 0? If A squared is minus 1, can A be equal to 0? No. Then clearly, okay, and hence A belongs to R mod I star. Now, what is A to the 4? If A squared is minus 1, A to the 4 is equal to what? Yeah.
Minus 1 or minus 11?
Minus 1. Minus 1. Minus 1.
Yeah.
Okay, what is A to the 4? A squared is minus 1. What is A to the 4? 1. Now, so A has order dividing 4. And R mod I star. Agree? Because A to the 4 is the identity of R mod I star, right? Are we good here? Please, is this good? Yes? People attending online, are we good? Okay. Now, can A be equal to 1 or not? If A squared is minus 1, can A be equal to 1? A is different than 1. since a squared is minus 1 plus I, which is different than 1 plus I. So what is the order of A? Does A have order 1? The order of A is not 1. Is it equal to 2? Is the order of A equal to 2? Is A squared equal to 1? No. And not 2. And what is it then? If it's order dividing 4, and it's neither 1 nor 2, what is it? 4. Hence, the order of A is 4. And R mod I star. Hence, the size of R mod I star is divisible by 4. So if I have an element satisfying this, then R mod I star, the cardinality, is divisible by 4. Now, what is the cardinality of R mod I star? It's 13 cubed minus 1. Is 13 cubed minus 1 divisible by 4? Wait. Is it F11 or F13? Oh shoot. I messed up. I messed up. Yeah, you have an element of order 4. You have an element of order 4, right? Because 13 cubed minus 1 is divisible by 4. Right?
It's not.
13 cubed minus 1 is so 5. 5 plus I. 5 is an element of order 4. Yeah. 5 plus I. It's 5 squared plus I, which is minus 1 plus I. Yeah. You see, I always, right? You have an element of order 4. Sorry about that. Yeah. Yeah. For 11, yeah, but the x cubed plus 11 doesn't work. Yeah, so, okay, let's change the question. Sorry about this. Yeah, no, I don't know why, I don't know what I had in mind. Oops. I messed up here. So you do have an element satisfying a squared is minus 1. It's 5 and minus 5. Okay, both of these satisfy a squared is minus 1.
125 isn't 0 by 13.
5 squared. 5 squared is 25, which is minus 1 by 13. You do have an element. I don't know what I'm saying. So let f of x, let f of x be an irreducible. Let's change the question. Reducible polynomial of degree 3 and f11 of x. Does there exist a in R mod I so that a squared is equal minus 1 plus I? Man, I messed up so badly. Well, look at this. If R mod I has 11 cubed elements, it's 11 cubed minus 1. And then what do you get? 11 cubed minus 1. Is it divisible by 4? 11 is converted to minus 1 by 4. Minus 1 is 0 plus 4. Okay. Is it clear or not? I mean, we did this yesterday with the t squared plus 1, right? Yeah. So if you have a field with 11 cubed minus 1 elements, you have an element of order 4. If you have a field with 11 cubed elements, do you have an element of order 4 in the group? No. Okay.
So if we have a of 11.
If you have a field with 11 cubed elements, do you have an element satisfying a squared is equal minus 1 plus I?
No, but 13 cubed, yes.
No, 11. 11.
We changed it.
Yes. Yeah.
Do you know that by the P is equal?
Yeah, by P is congruent to 3 mod 4 or P is congruent to 1 mod 4. But is it clear that a squared minus 1 plus I is an element of order 4? If P is odd, that's the key part. Okay. Why did I pick 13 though? Shoot, I know what happened. I had x cubed minus 2 is equal in F19 of x. This was my example, x cubed plus 17 in F19. Then I said if I want to do the calculation in class, it's going to take a long time. Calculation of F13. This is what happened. If I have a good memory. So, okay, so let f of x be an irreducible polynomial of degree 3 in F11 of x. Does there exist a in R mod I such that a squared is minus 1? What is the answer? No, because if you have such an element, it would have order 4 in the multiplicative group. Now, does 11 cubed minus 1 is 11 cubed minus 1 divisible by 4? No. So you don't have such an element. Is that clear or not? I mean, we did this yesterday. You remember this or not? With the field set 3 cubed, and we showed that t squared plus 1 is irreducible in that field. Because it has no roots. Because if it had a root, you would have a polynomial of order 4. A degree, an element of order 4 in the multiplicative group. Okay, so sorry about that. That's okay. No problem. The question will reappear on your practice final. So it's a good, this question will reappear on the practice final, so you could practice it again. And I think the answer there is no. Okay, that's this is why. But this one is a bit harder. The other one is a bit harder. Okay, yeah. So do you guys have questions on the course, on everything, or no? Questions? Yes. Of D4. Yeah, so the question is how to find the conjugate class of D4. I mean, there are many ways. That's why I don't ask. So R mod I has no element A satisfying A squared is minus 1 plus 9. Okay, so sorry about this one. It's a mistake. Well, it's a big mistake. So easily fixable. You can change the prime number, and then all will work. But then you will have the chance to practice this in your practice final as well. Okay, but do know this. It's an important fact. This elements of order 3, order 4, a squared plus a plus 1, a squared equal minus 1. These are good things. Okay. Yeah. Like something to you?
It's just at the end.
Oh, do I? I don't know.
Just didn't.
I don't know. I don't know. Did I do less? Okay. Okay. No, I mean it doesn't matter. Okay. Don't worry about it. If I did less, then that's okay. Okay. Oh, what were the questions? Did I miss questions?
You just didn't answer this.
Does it print on one page? No, but does the paper print on one page? If you print it? If you print the SI, maybe I looked at one page basically, and then I forgot those two. Yeah, but don't worry about them. Okay, I can tell you don't worry. But I mean, don't worry about it. If I forgot them, then they're probably not important. What is it? But what are the questions? Oh, doesn't okay. I don't know what.
There's all of this.
So what are the questions?
All of this. Hit answer.
All of this I didn't answer.
Yeah.
Oh, so the 4th and the 5th I didn't do. Okay, so 4 you can do because it's homework 8, right? Next homework, you have how many homomorphism from Z mod M to Z mod N. And then find all the possible homework. Okay, so that you can miss the 5th one. Okay, that's one less. Okay. This one less. It's weird. I don't know why I didn't.
Also, you did it in a review set.
I did in a review session. Okay, maybe. It's weird. Okay. Anyways, one less thing to study. One less. But okay, so how do I find the conjugate class of D4? That's a very good question. The idea here, you have many ways to do it. Many ways to do it. Now, what I would do first of all is use the orbit stabilizer. First, you know that the conjugacy class of D4 must have size dividing 8 because it's a stabilizer under the action of conjugation. So a conjugacy is it's an orbit under the action of conjugation. So it must have size 1, 2, 4, or 8. Okay, 8 you can eliminate, right? Because 1 is alone, so you cannot have a conjugate class of size 8, right? So the possible size are 1, 2, and 4. Okay. Now look at the identity. The identity is alone. Now, start eliminating. One way to do it is write down D4 as cycles. Okay? So label your square 1, 2, 3, 4. What do you have? You can write it as identity, vertical, horizontal. What is the vertical reflection? It's 1, 2. That's 3, 4. H is 1, 4, 2, 3. You have the diagonal D1, which is 2, 4, and the diagonal D2, which is 2, 3, which is 1, 3. And then you have the rotation 1, 2, 3, 4, and then the square of the rotation 1, 3, 2, 4, and then 1, 4, 3, 2, and then what as well. That's it. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now you know if they're conjugated in D4, then they're conjugated in S4. So they must have the same cycle shape. But that doesn't mean they're conjugate if they have the same cycle shape. It doesn't mean they're conjugate in D4. So at most, any conjugacy class, so these two, they're either alone in their conjugacy class, right? Or they're both together. This is R, right? Yes. Yes, exactly, but not in D4. So now, D4 is non-abelian, and what is the order of D4? 8, right? D4 has order 8, and is non-abelian. So what is the size of the center of D4? If you have a non-abelian group of order 8, then its center must have size 2. Why is that? Because G modulo the center is not cyclic, right? So the center cannot have size 8 and it cannot have size 4. And it's a 2 group. It's a P group for P equal 2. So the center must have size 2. So you have an element of order 2 in the center. And that's it. Okay, so an element of order 2 in the center means that you have an element of order 2 that is alone in its conjugacy class. That's R squared, which is this one. So you have 1. So this is R squared. So you have 1 alone. And then you have R squared alone. Great. Pardon me? Not together. No. It's in the center. Then every element in the center is alone in its conjugacy class. So you have 1 and R squared. Now what do you get here? Now we have to look. So any other conjugacy class has size 2 or more. Okay? Great. Now look at these two. This is R and R cubed. Can R be alone? No, because these are the only ones. So it must be conjugate to R cubed, and that's it. Right? Because they have the same cycle structure and they're alone in their class. Great. Now, let's look at the others. Now we have here 4 elements. Look at V. This is this is D1, say. This is D1, and this is D2. They have the same cycle size. The conjugate class has size at least 2. So this must be this must be one conjugacy class. D1 and D2. And V and H must be in their conjugacy class as well. Right? That's the conjugacy class. Normal subgroups. These are a union of conjugacy classes. So what you can do, you take the subgroup generated by R. That's a union of conjugacy classes. It has index 2 as well. So right? One R squared is a subgroup of order 2. Then what do you have? So you really don't have any other choices except taking one R squared, D1, D2, and check if this is a normal subgroup. Is it a normal subgroup? It is a normal subgroup. It is a subgroup. So 1 R squared, D1, D2. This is because D2 is R squared times D1. And the same thing, you get 1 R squared V and H. Okay. These are the normal subgroups. No, you have one more. No, that's good. That's good. You have one more. No, that's good. These are normal. And you have 1 and D4. 1 and D. No, okay. Is that good? These are normal subgroups of D4. But I won't ask you to justify it because justifying it is a bit painful, They'll just tell you this thing. Okay? Yeah. Where? It's R squared V and H. Yeah.
Do odd n-gons only one element in this?
Yes, they have just have the identity. That's right.
And if it's a multiple of 2,
It's
one
1.
larger than 8, is it?
So it would be, so if you have a 6 gon, say,
Yeah.
it's 1 and R cubed that are in the center.
Okay.
So the center has always 2 of if n is odd,
Yeah.
if n is even, sorry.
Yeah.
If the n gon is even, if you have an even-sided polygon, then the center is 1 and Rn over 2.
Okay.
And if n is odd, the center is just 1. But not the same proofs, definitely.
Yeah.
Definitely. It is. Then you have more calculations to do. Here, you're just doing it quickly, using this fact it's a 2 group. You can go quickly. Yes. The index can have index P in any non-abelian. Sorry, the index. Oh, okay, so 1, yeah. So the index can't have index, cannot have prime index, yeah. Right? Because if G mod Z G is cyclic, then G is abelian. So the center has index 1, and 1 is not primes. Unless you consider 1 to be a prime, which in this course we don't. Okay, 1 is considered not to be a prime in general. Some people consider it to be a prime, but it's very tiny minority. Okay. Yeah.
Does every element have to be be paired up in this class?
Of course,
Okay.
because every element has an orbit.
Oh, yes.
Okay, every element has an orbit. Now it's not necessarily alone. It's only the center that is alone. Yeah. Questions? More questions? People online, do you guys have questions on the notes?
For some of in class, some of those things, it's like you're saying, we need to prove left as exercise, is that?
Don't worry about it. Okay. Yeah.
Just checking, V is the group where
No. V here is the vertical reflection. V is the vertical reflection.
but I mean the Klein thing.
Oh yeah, it's the group with the three 2 cycles and the identity.
All the 2 cycles in there.
All the 2 by 2 cycles.
But
So this is the Klein for group and what they call the Klein for group.
1, 2, 3, 4, 1, 4, 2, 3,
Exactly. And this is a normal subgroup of S4.
and how do you prove that?
Because
you do.
it's a subgroup, right? If you call this A and you call this B, then this is equal to AB, and this is also equal to BA. And you have one AB is equal to BA, and A and B have order 2. This is a subgroup.
If these exist. You also say ABA inverse is in B. No, what is it?
So if X is in V and Y is in S4, Y inverse is in V.
B.
I mean, it's a union of conjugacy classes in S4. So once your proof is a subgroup, it's a union of conjugacy classes in S4. So you could do that. Now in the practice, I ask you questions about this one, right? I ask you questions about this one. Compute the centralizer, compute things like that. Very nice. And then I ask you a nice question at the end. Construct a surjective homomorphism from S4 to S3 using this point.
Could you ask us to do like from S5
To S3
or S4?
doesn't work.
Oh.
S surjective 1 doesn't work. What are the only normal subgroups of S5?
A.
Okay, so if you have a surjective homomorphism from S5 to a group, the kernel is either S5, so the homomorphism sends everything to the identity, right? Or the kernel is A5. This means that the image has size 2, right? Or the image is 1, or the kernel is 1, so the homomorphism is injected. Okay, so you cannot find a surjective homomorphism from S5 except to S2 and S1. S4 is really special because you have that normal subgroup of size 4. The normal subgroups of S4 are 1, this thing, A4, and S4. This is a fact that you can know. I mean, you can use this fact without proof. Things if you have to use it. Okay. Yeah. I mean, it's better to take the notes from someone. I don't think I'll have the time to upload a recording. Well, yeah, because the recording is, I don't know what happened. I mean, it's the Euclidean. If you understand the Friday and Monday's lecture, I think it's not a bad. It's okay. Okay. Yeah. Yeah.
Do I appear?
No.
Here, I don't really understand the proof of this proposition because of this. Maybe I wrote it wrong, but it's like the order of one part in
R plus divides M. Exactly.
no, but like
Order of 1 R in.
Oh,
Yeah.
yeah.
Okay. How do you say? Could you do another example of finding the order of some polynomial in a quotient ring? What do you mean the order? Could Amir? It could be both. It could be a big proposition, or it could be a big theorem, or it could be a small proposition. Yeah, Maya, what do you mean? And Cynthia, is it similar or not? How would be similar? I don't know. I mean, I'd say, if you were to put them together, I'd say it has 50% similarities, topics covered, and things like that. To be conservative. Now, the thing is that I don't want you to look at the practice final and then study. Okay. I don't want you to look at the practice final and study. That's what I don't want you to do. Okay. Cynthia, is that okay? I don't want you to look at the practice final and study. I want just the practice final to be a test of what you think on how you studied. But I don't want you to say, okay, I didn't do this question well, let me revise it. Okay, this is not, I don't think that's the proper way to do it. Because, I mean, some questions might reappear and some questions might not. So it's not necessarily the same. Okay, does that answer your question? But the practice final is a bit harder. Yes. Yep. Yes. I didn't prove it in the notes. Left is an exercise. Now, is that the lecture where the recording messed up? Is that one of the lectures where the recording? Yeah. So I think that okay. So in the notes, I didn't do it. Yes, I think. No. Is it 1R? So R has characteristic 0 if and only if 1 has infinite or doesn't have finite or. But I think I proved it. No.
You proved it verbally. Yeah.
No, I think that's the.
It's in the video.
You proved it verbally. That's what I One does not have finite order in R plus.
Yeah.
Oh yeah, you just said. You said it.
Okay, then I said it. Oh,
But like,
You didn't write anything down.
yeah, okay, sure.
Yeah, if we don't.
Oh, no, it's important. It's important. Everything in characteristic is very important. But that doesn't count as F as well because I said I would do it, right? I remember I had two proofs, right? Two proofs that day. And then a finite field had order p to the n for some n, right? I had,
Yeah.
right? Okay, you have the lecture number? Because it could be in the video. No, it's not in the video? Okay, so let me just do it. It's proved, right? R has characteristic 0 if and only if one R does not have finite order in R plus. Okay. Right? So R has characteristic 0. If and only if phi is injective, where phi is the unique ring homomorphism, right? From Z to R, right? If and only if M times 1R is different than 0R. Or me here, I think I did prove it. I remember having proved it, no? No? If and only if phi of
you said whole- no.
I said how to okay. I didn't write it. Okay. So if and only if phi m is different than 0R for all m different than 0, right? Agree or not? Yeah? This is what's meant to be injected. That the kernel is non-zero, so phi of m is different than 0. And only if m times 1R is different than 0R for all m is different than 0. Right? And if and only if 1R doesn't have finite order. Okay? Is that clear? Okay? Yeah, so if you have two quotient strings that are not fields, how could we compare them to tell if they're isomorphic or not? Don't worry about it, okay? No, I'm just answering someone online. You like when I say don't worry about it, right? Okay, yeah, don't worry about it. We didn't do many examples. But then, for example, C and R, for example, these count. These you should worry about, for example. But quotient rings is a bit more difficult here. I'll not ask you to prove whether two quotient rings that are not fields are isomorphic or not. Okay. Yeah, especially you're talking about polynomials, you mean. You're talking about polynomials quotient by an ideal in the polynomial rings. Is that what you mean? Yeah, so yeah, that's a like 25 times. Yeah, we did an exercise like that 25 times with a R mod I, but every time we had one is a field and one is not. Oh, no. Yeah, don't worry about the other options. If I give you an exercise like that, one will be a field and one won't be a field. What do you mean, whatever?
Oh, yeah.
Exactly. And one is not a field and one is a field, so you could say that they're not isomorphic. That's how we should go. And then you check irreducibility. No, I think it's gonna be nice. It's gonna be good. I think it's like I have a good feeling about this. I don't know why. I think I got maybe half the material. Not really.
Complex
Don't worry.
numbers.
He said,
So,
But you can still put complex numbers like make a in like a ring.
C of I, for example, C, yeah, but just I won't ask you questions about complex numbers. I just ask you just I squared is 1. That's it. I squared is well. I squared is
Okay.
yeah. I squared is 1. Minus 1, minus 1.
That thing, you know, the Q8, there's one.
Yeah.
I
squared is minus 1 there.
squared one then.
Minus 1. Minus I squared is G squared is K squared is minus 1.
And J squared is also minus,
All the squares are equal to minus 1. Yeah.
except one.
Except for 1 squared. That's 1. And then and minus 1 squared is 1 as well. So 1 squared minus 1 squared. J, yeah, everything else squared is minus 1.
Yikes.
No, I wouldn't worry about Q8 because I didn't do it in class. I did it once maybe, and that's it. But don't worry about it.
There's no Q8.
And group action is super important.
Yeah, group action is very important.
And do we have to know like the isomorphism and homomorphism for like group part?
Yes, yes, you have to know these. You have to know these. These are perfect for proofs as well. For the first question, I can ask you from a homomorphism part. And I've done some examples here, right? What did I do?
Z, like.
No, this won't be a proof question. A proof will be something I did from the notes. Like for example, phi of G inverse is phi of G inverse, phi of identity is the identity. Yeah, the kernel is a
oh,
subgroup.
I was, yeah.
The kernel is a subgroup. The kernel is a normal subgroup. And then phi is injected if and only if the kernel is the identity. That you can expect questions like that. You can expect. Yeah. Also, you can expect Celo's theorems. You can expect many things. You know, I'll leave you. You know the I won't cut it for the. I didn't say conjugation. Did I say don't worry about it?
No.
No. You definitely have to worry about it. What is two
Oh,
homes?
In the review, you said.
Cauchy or like.
Cauchy maybe. Cauchy. Conjugation, I said not important. No, conjugation, very, yeah, very important.
Maybe don't worry about Cauchy. So.
I said don't worry about the proof of Cauchy, yeah.
Stamen, yes.
Same, yeah. Anyway, I mean, I cut half the things already. Well, not half the things. I cut a fair bit. 5 things, 6 things.
It's a hundred pages, but that's smaller.
Yeah, but I mean,
Maybe
but yeah, I mean, the first part, the first half, you will not get any proof of it. You may use them. You will have to use maybe small bit of it, or you can, yeah. But again, almost everything can be done with the second half of the course. That doesn't mean that the first half is not useful, but almost every single question can be done with the second half of the course. Okay. Yeah.
Unrelated, but yesterday we were doing a problem with like 4m factorial.
Yeah. Don't worry
We
about it.
did it. No,
Yeah, I didn't do it today. Yeah, I forgot. I didn't have time. Yeah, don't worry.
don't worry about it.
There's a problem that I said. It's an interesting problem. That's when I say interesting, everybody thinks about the final. So like,
No, I'm just curious about the proof.
yeah. So what you do is that, so you know that 4m factorial is minus 1. On P, right?
Yeah.
You just write it's 2m factorial. And you just write it's 2m plus 1 times 2m plus 2m. Right?
Oh, you just break it.
And then 2m plus 1. So you know that 4m
Oh,
into 0. So 2m plus 1. What am I saying? So 2m plus 1. So no, 4m plus 1, sorry. as 0, right? Because
Yeah,
p is 0 mod p. So 2m plus 1 is just minus 2m. Okay, so this is just 2m factorial times minus 2m.
Yeah.
Times minus 2m minus 1, right?
Yeah.
And then, sorry, then minus 2m plus 1 here. And then you get minus 2m plus, so you get 2m minus 2m minus 2m plus 1. And then you get 4m, which is 1, right? Because minus 1 might be. Right?
Last step.
So you get 4m. Oops. The last step is 2m plus 2m. Which is 4m, and it's
okay.
going to minus 1.
Okay.
Which is minus 1. Now pull out the minus from every single one of them.
Yeah.
Minus 1, minus 1, minus 1. You get minus 1. How many minus 1s you have? You have 2m, right? Times 2m factorial. And you're left with 2m factorial here. Okay?
You be tutoring Algebra 2 or TA2?
I'm not taking algebra 2, you know. I think Julian and Antoine are. They might be. They might be. I don't know. I don't know. I don't know. I don't nothing. I'm not taking them. No.
PhD.
Yeah, I hope so.
What? If you graduate from teacher, you still stay here and teach us, or like?
It depends. I mean, let's see what life brings. So
Does Silicon Valley make them like quad?
let's finish what you have here first. And then let's see. Okay, so yeah, let's see if people have questions. If we do well for group review, ring practice, and review final, would we be okay? What if we have harder time for homework question? No, I mean it's again, you just should be comfortable with the exercises. Homework are more important than the review, I would say. Okay, and the ring practice could count as a homework. Okay, if this is the question. So no questions about complex numbers, no. Pardon me? No, you have no complex numbers will be mentioned. Okay. Yes. Did you guys fill in your course evaluations? Yeah. Okay. Okay. So any more questions? Yes. Okay. It cannot be isomorphic. It's 4 mod per row. You get that. Okay. So row is surjective. Okay. Row is surjective. Then you got it.
So that's it.
Row is surjective. Then I can ask you write down what per row is, for example.
So like. It's just.
Is row. And you know that S4 modulo the kernel, you managed to show it's isomorphic to S3, right? Which is S3. Okay. Size, very good. Also, the S4 mod per row is isomorphic to S3. And then I can tell you what is per row. Yeah, exactly. It's the homomorphism induced by the action of S4 on S4 mod H. Yeah, row. But you cannot write it down explicitly every element because it's induced by an action. If it's induced by an action, you have to spend some time writing it down. No, you can do this independently from knowing what the kernel is. Because S4 modulo the kernel has size dividing 6. Right? So
Because it's three, which is that.
exactly. S4 mod, which is row S4 divide 6. At the same time, when you showed that your H is not normal, and you know that rho is contained in H, agree or not? The H is a subgroup of order 8, that the H would be. Now you showed that H is not normal, right? Yeah, if you show that H is not normal, then rho has size strictly smaller than H, because rho is normal. Agree? So rho has size strictly smaller than 8. Agree or not?
Yeah, so it's bigger than, the index is bigger than 3.
Strictly bigger than 3. And it divides 6.
So it's 6.
So it's 6, exactly. So what is the size of rho? So S4 mod rho is isomorphic to S3. S4 has 24 elements. S3 has 6 elements. What should be down there? 4 elements. Now rho is a normal subgroup of S4. What is the only normal subgroup of S4 of size 4? Cycles. The three 2 by 2 cycles and the identity.
Why do we know the size is less?
The size is less. H is not normal. Right? Your subgroup you're acting on is not normal. Rho is normal. If the sizes were equal, then rho would be equal to H.
But what if it's bigger?
No, because the kernel is contained in H. What is the kernel of rho?
Oh, yeah.
It's the intersection of X, H, X inverse. As X belongs to S4, where H is your subgroup of order 8. Is that clear?
So I could
That doesn't. No, rho is surject, not an isomorphism. Rho is a homomorph. Yep. Yeah, rho cannot be an isomorphism from S4 to S3. Okay. Rho, but you have an isomorphism from S4 modulo the kernel to S3. Maybe that's okay. And then I can ask you write down rho, for example. You have to write down what rho is. If I ask something. If I ask something like that. Okay. I did this example how many times? Yeah. No, that's okay. That's okay. Yeah, no, did I write? I write search up. Oh, okay. So you read it and then okay. Yeah, and that's and then you can do it in many ways. Okay. Did you do exercise 1 from yesterday's stream from the second ring sheet, or we do? No, I mean the first 2 exercises. I think the first one I did verbally, exercise 0, how to construct them, and everybody was okay with them. I think so. And the second one is x to p minus 1 minus 1. I also did. Yeah, I did them in yesterday's stream. Yes, I did them. No, I am. Okay. Questions? Yes, there are definitely. No, the rest of them are PDFs. It's in the same PDF. Yeah, homework 8 and 9 have answer. Homework 9 doesn't have answers. No, 9 doesn't have an answer. 9 I did in a recording. 9 did in a recording. 9 I solved the questions. Really? Really? Okay, no, 8 has solutions. 9 has solutions because I did them here. 9 you had the solution before the so 9 you had the solutions before. 7 I did a recording. I did record it before. I did record it after. I recorded what one? When did I post it? The weekend. Yes.
Like we know that like our mathematics is 13 to 3 elements,
Yeah.
but the unit group of that,
You want to find the unit group of that?
but like our mod I star
Yeah.
has 13 to the 3 minus 1.
Yes.
Is that applicable to every single? Okay.
What is the group of units of the field? It's just the field minus 0 because every other element is invertible.
Okay.
Is that question clear with 13 replaced by 11? With the so a squared is equal to minus 1 correspond to an element of order 4, right? If the field doesn't have characteristic 2, so if 1 is different than minus 1. Now, if the size of the group of the ring has size not divisible by 4, did you have an element of order 4? No. We did this yesterday. You remember this? When we say construct a field of 20 with 27 elements, do you have an element such does t squared plus 1 has a root in this field or not? You remember this question? Construct a field with 27 elements. Does t squared plus 1 has a root in this field? We saw that if t squared plus 1 has a root, then I would have an element of order 4.
And d to 20 to the power of 24 or something. T to the power of 24.
That's a different one. That's a different one. Yeah. That's so it's the additive order of 1. What's the additive order of the identity or negative identity? One plus I. Yeah. But is that example clear? Everybody, is that example clear?
But we said it is divisible by 4, right?
No. So if you have an element of order 4,
Yeah.
then this is divisible by 4. Now my
You're
choice
saying
of
there's no element of order?
exactly. So you have no such element. And because I changed the R.
Oh, so it should be, it's not.
No, I changed the R from 13 to 11.
Yeah, so with 11, it should be it's not divisible.
It's not divisible by 4. Is that clear?
Yeah, my other thing is, how did you get from 11 cubed minus 1 to like minus 1 cubed?
11 is congruent to minus 1 at 4, right?
Oh, yeah.
So 11 cubed is congruent to minus 1 cubed. Okay. 11 cubed is congruent to minus 1 cubed. So minus 1 you get 2 mod 4. But is that example clear? Forget about the 11 and 13. Is the a squared equal minus 1 plus I being of order 4? Is that clear?
A is a more offensive, yeah.
A of order 4. But that's important, please. Yeah. Plus 1. That's yeah. Yeah, no, you cannot. If it's different, then you cannot do it. It's a special polynomial. Yeah, yeah, it's a special polynomial. It doesn't work with that. Where here?
This next step A2 of 4. A2.
Why does the order divides 4?
Yeah.
If a to the 4 equal 1, if g to the n is equal to the identity of the group, then the order of g divides that n. If g to the k is equal to the identity, then g has finite order and that order divides k. Right? You remember this?
So we basically want to find the order of the element, and then we want to see if the size of the groups of units is divisible.
And
then if it is,
Exactly.
it does contain, and if it
Yes.
isn't, it does not
No.
contain.
no. If it's not divisible, then it does not contain.
Oh, and then if it is divisible.
If it's divisible, if it's a field, the thing you're talking about is field, then it does contain. Yeah. But we're not in charge of it.
So just if it's not divisible,
Then,
it doesn't contain.
So if you have g to the n is equal to the identity in g, then g has finite order. If you have, say, x to the n is equal to the identity, then x has finite order and the order divides n. This is from the pre-midterm part. Remember this?
Why are we looking at the order?
Sorry,
of-
just
Oh, sorry.
you remember this or something about it? I mean, we could use it in Lagrange. We did it before Lagrange even before Lagrange. I think it's lecture 10. So x to the n is equal to the identity if and only if the order of x divides n. Okay, so x to the 4 is the identity, a to the 4 is the identity, then a to the 4 is the identity, then the order of a divides 4.
Oh,
Okay, that's it. Should I do another example of this one? Should I do another example of this one?
Yes.
Yeah, let us do that. So let's I don't know.
when sorry, Cauchy's Looney's statement, but Paley's statement proof.
Yeah, and you should know these. So let f of x of degree 3 and f1 over 3 of x. Okay? f1 over 3 of x. f of x is of degree 3 and f1 over 3 of x. And let I be the ideal generated by f of x. Let me shut the door. Thank you. Let's call this R. Does there exist?
Is it F 103?
103 is prime number, right? Congruent with 3 mod 4. Does there exist A in R mod I? What's that? Okay, that's the question.
And just to be sure, you're saying that F of X is a generator of,
The ideal.
Yeah.
Is a principal ideal generated by f of x. Exactly. Does there exist such a thing? How do I do that? Well, yeah, I mean, homework 7-9 is going to be more important. Now, in the reviews, I re-emphasize these, right? I re-emphasize a lot of concept from homework 7-9, right? Just so that you know, if you reviewed already homework 7-9, they'll be in your head more. Okay. So does there exist an element A in R mod x such that a squared is equal to -1 plus I? So first of all, f of x is a reducible polynomial of degree 3 and f1 over 3 of x, and I is f of x. Okay. What can I say about R mod I? R mod I is a field, right? R modulo the ideal generated by f of x is a field, right? Is that clear or not? With how many elements? R mod I is a field with 100 cubed 3
because F of X is irreducible.
degree 3, right? Very good. Now, suppose R mod I a squared is -1 plus I. Is A equal to 0? A is different than 0. Really, A is different than 0 in R mod I. What is the 0 in R mod I? Just 0 plus I in the ring, right? Okay. Hence A belongs to the group of units of R mod I, because R mod I is a field. Since R mod I is a field.
Because you're excluding 0.
Exactly. And in a field, every non-zero element is a unit. Every non-zero element has a multiplicative inverse. Very good. Now, great. Now, is A equal to 1 plus I or not? No, because if A is equal to 1 plus I, what would A squared be? 1 plus I. Yes. A squared is equal to -1 plus I. Is different than 1 plus I. Now, what is A, and A squared is different than 1 plus I? Clearly, right? Clearly, right? Because 2 is not equal to 0 in this ring. What is equal to 0? What is the characteristic of this ring? What is the characteristic of this field, of this ring? What is the characteristic? The quotient ring, what is the characteristic of it? 103, right? Take 1 plus I. How many times you need to add 1 to get 0? 103 times, right? So 2 is different than 0 in this ring. So a squared plus 1 is different. Now, what is a to the 4 in that case? A4 is equal to a squared squared is equal to minus 1 plus I squared is equal to 1 plus I. So far, so good. Because if A4 is 1, then the order of A will divide 4 with either 1, 2, or 4. Okay, so A and R mod I star has, of course, multiplicative, and of course, order 4. Order dividing 4. Let's write this instead. Order dividing 4.
But didn't we just deduce that it's 4 and not another?
Exactly. No, I'll just write it down. Yeah. Since A is different than 1 plus and A squared is different than 1 plus I, then A has order 4 and R mod I star. So if you have an element satisfying A squared is equal to minus 1, then its order would be 4. Right? In this ring. Now what can I say then? Hence R mod I, hence 4, will divide R mod I star. Look right now, oh well, the star is inside. Which is 103 cubed minus 1. Why is it 103 cubed minus 1? Why is the cardinality of R minus I star 103 cubed minus 1? Yeah, and why do I get a group under multiplication if I remove 0? Because it's a field. And every non-zero element is a unit. Very good. Now is 103 cubed minus 1 divisible by 4? No. You see that? So 103 cubed. 103 is congruent to minus 1 but 3, right? Agree or not? No, 103 is congruent to 3 mod 4, right? 103 modulo 4 is what? 3. Right? What's the closest multiple of 4 to 103? 100, right? 103 is congruent to 3 mod 4. Is 103 minus 3 divisible by 4?
Yeah.
Is 103 minus 1 divisible by 4? Yeah.
No.
No, it is. 103 minus 1. So 103 plus 1, which is 104, is divisible by 4. So 103 cubed is congruent to minus 1 cubed mod 4. So 103 cubed is congruent to minus 1 mod 4. So 103 cubed minus 1 is congruent to minus 2 mod 4. It's congruent to 2 mod 4. Is 103 cubed minus 1 divisible by 4? Is 103 cubed minus 1 congruent to 0 mod 4? Minus 3 mod 4 is the same. It's 2 mod 4. Yeah. Add 4. Add 4 to minus 2. Yeah. So is 103 cubed minus 1 divisible by 4? No. So can 4 divide 103? Okay, is it clear now or not?
The example, just like calculate the number, actually show that.
Yeah, you can calculate it. Yeah, but if I give you a very large number, so if I give you something like 103 cubed, are you able to calculate it? Yeah. No, I mean, I'll be reasonable, but sometimes just so let's say if let's do a small game now. I give you a polynomial of degree, irreducible polynomial of degree 3 in F19. Okay? In F19 of x. 19 is prime. Does F19 of x modulo that polynomial, the irreducible polynomial of degree 3, does it have an element satisfying a squared is minus 1 plus I or not?
Size 5.
But no, degree 3.
Does it have an element size? And then
No, such that a squared is minus 1 plus I. No, because 19 cubed minus 1 is not divisible by 4. Exactly. 19 is 3 mod 4. Exactly. So because you can just look at the residue plus mod 4. 19 is minus 1 mod 4. So once you cube it, 19 cubed minus 1 will be congruent to 2 mod 4. So if I give you, let's see, 43, f of x an irreducible polynomial of degree 5, and f43 of x, could you find an element such that a squared is equal to minus 1 plus I and do quotient ring that has 43 to the 5 elements or not? Why?
Because same thing. It's 4
Yeah.
minus 1. 42. Still not divisible.
But what is still not divisible by 4? You have 43 to the 5 minus 1 here. But it's still the same because 103 to the 5 and minus 1 to the 5 is still minus 1.
Okay.
Okay.
I'll just do multiple.
Exactly. It's better. It's better to do it. Okay, let's say 27. I give you an irreducible polynomial of degree 3 in F3. Do you have an element so that a squared is equal to minus 1 plus I? And F103 divided by that irreducible polynomial of degree 3 or not? No, so you have an F3, a polynomial of degree 3 that is irreducible. Does the quotient ring contain an element such that a squared is equal to minus 1? F3 and degree 3, irreducible. Does the quotient ring contain an element such that a squared is minus 1? Why? No, but what do you answer? What do you answer?
Minus 1 is not.
27 minus 1 is not divisible by 4. Exactly. No, this is because if you have an element such that a squared is equal to minus 1 plus I, then this a must have order 4 in the multiplicative group. Minus 1, exactly. Yeah, a squared plus a plus 1. That has order 3, for example. We did this today. Yeah, yeah, exactly. Exactly.
It's congruent to 3 more 4. Do it like that.
Depends on the question. Depends on the size of the field, right? Depends on the size of the field, right? The size of the field. Not necessarily. So take Z103 of x. So take Z3 of x, divide by x squared plus 1. So F3 of x modulo x squared plus 1. That's a field. It has degree. Okay. Yeah. So the field. Yes. Very good. Very good. Very good. So if you have a number p congruent to 3 mod 4, and you have a field of size p to the n, where n is odd, then this field does not contain an element of order 4, like an element whose multiplicative order is 4. Yeah. Very good. Very, very good. Yeah. You're looking at the degree of the polynomial, basically. If the degree of the irreducible polynomial is odd, then this doesn't work. Then then you cannot have an element so that a squared is equal to minus 1. Very good.
Can you explain quick how you know why a squared plus a plus 1 has order 3?
Yeah, multiply by a minus 1, what do you get?
The,
A cubed minus 1.
AQ minus 1, yeah.
but how does that say that?
If a squared plus a plus 1 is equal to 0, then when we multiply both sides by a minus 1, you get a cubed minus 1 is equal to 0. So you get a cubed is equal to 1. And if a is different than 1, then a doesn't have order 1. You see that or not? Should I write it? Yeah.
Wait, if a cubed equals 1, then a is 1.
Yeah, this is why I said p is bigger than a to have order 1. Right? But a squared plus a plus 1 cannot be 0 because I said that p is bigger or equal to 5. Okay? Okay, if p is bigger or equal to 5, does plugging in 1 give you 0 or not? No. Okay. So a is different than 1. Agree? So a is different than 1.
Yeah.
Now multiply this, a minus 1, a squared plus a plus 1. What do you get? This is 0, right? Agree? This is
Oh,
0.
because 0 times something 0.
Exactly.
Okay.
So a cubed is equal to 1. This means that a has order dividing 3, has multiplicative order dividing 3.
Oh.
But a is not 1. So a must have order 3. Is there anything with polynomials inside? No, just groups.
I thought we agreed that a and 1.
It doesn't have order 1. Like you multiply a to the 3 and it gives you the identity.
Can I clarify? Sorry, can you clarify why is
So
x cubed? Jan, the homework 9 have been solved before in a recording. That I solved homework 9 before it was due. There's a recording for that, and then you can see it on the lecture by lecture. If you go to course outline, there is lecture by lecture, and then I post everything. Yeah. So all the solutions you have them either in recordings or in PDFs. So Monday's class, we did an example to construct a field with 8 elements. Can you clarify if, this question? Oh, can you clarify x cubed plus x squared plus 1? Yes. You need a polynomial of degree 3 that doesn't have roots. And this is why x cubed plus 1 doesn't work, because when you plug in 1, you get 0. That's right. Yeah, Cynthia, that's right. Okay, Jan, yeah, that's good. No, that is good. Very good. Yeah, the amount. Yeah, sure. Yeah, I mean, I reduce it, right? Instead of giving you 9 homeworks, I gave you 3, 4 homeworks. It's yeah, but again, you will see on Friday. It's not that bad. It's not that bad if you studied, and you should trust my word. So study the group homomorphism parts and the groups. Don't forget the easy parts of group. For example, kernel is a subgroup. Kernel is a normal subgroup. Injective if and only if kernel is 1. Phi of identity is the identity. Phi of G inverse is phi of G inverse. Right? You know the proof of Silo's third theorem, but you don't know these basic things. This is this would be
Now the time to prioritize.
yeah, but I mean, you have time. You still have time, especially if you're comfortable with the other things. You should be comfortable with the easier things.
So now I asked my flatmate who's in psychology, and I said, "What do you recommend to like learn like a really long to like make it into like a personal story? It's like a memory. I can't think of stories to like memorize Silas third theorem. So I was hoping you had any ideas like stories.
No,
Okay.
no. But again, you will see on Friday that it's going to be fair. Okay. Some of you will find it too easy. I can tell you. Some of you will find it too easy. Who's- Oh, Peter. Oh, okay. I don't know. Okay, yeah, okay, yeah. But I mean, again, are we good with studying? Did we finish studying? Finish studying. No, but I mean the theorems. No, the theorems. Are we done studying the theorems? Characteristic part, did we study them? Group homomorphism part, did we study? The proofs, for example. If I ask you, show that the kernel is a normal subgroup, you know how to do that. Oh, right now. So that the kernel is a subgroup, you know how to do that. So define the kernel, you know how to define that. Show that phi of identity is the identity, we know how to do that. Yeah, those are the notes, right? If I tell you prove Silo's second theorem, you know how to do that. Yes. Yeah. But I mean, but that's why we should study these. Okay. If I tell you prove Silo's third theorem.
For the middle, so big, we just assume that, like, they, say from the homework or like. No, I'll be clear, because like that part, we have to prove the homework first with another page long, but the stylus. No. See, you can assume them. I mean, you won't have to use them, you just have to prove them. State and proof, that's what you have to do. Part, the NG, so NG, that part, it's like. It's long? No, that part is like, that part is the homework. I'll show it. Yeah, no, you can assume it. I see what you say, I see what you're saying, yeah, you can assume it, yeah. Yeah, you can assume it, it's not you can assume, as long as it's really not the main part. I mean, yeah, at the practice final, I actually prove one part of the CELO third theorem. I ask you show that the number of CELO P subgroups is congruent to 1 mod B. It's not the whole proof of the CELO third theorem, but it's one part of it.
If we're asked like the second, like the final part of the CELO third theorem, do we have to show, like, prove why size of S is equal to index of G? Yeah,
I would say in part A, for example. In part A, show that G acts transitively on this, and right?
so we're not specifically asked.
Yeah, if you're not specifically asked, you can assume it. You can just say a word from it. By the orbit stabilizer, I know that G yeah, exactly. Okay, but the characteristic part, everybody should be ready for the characteristic part. Okay, study the characteristic. You'll have a proof from that. And the proofs there are very short, right? And the proofs from group may be long, may be short. And then you have a proof from the beginning of the fields. So people who are listening. So we know how to show that, for example, if a ring, if 1 is equal to 0, then the ring is 0. If what else? Exactly. If R is a commutative ring, if R is a commutative ring, then R is a field. If and only if its only two ideals are 0 and R. Yeah. If R is a finite integral domain, then R is a field. A finite integral domain is a sorry, yeah. Yeah. So if R is a finite integral domain, then R is a field. A field is an integral domain. We know how to prove that. That's easier, right? Because you have the inverse. We know how to prove these or not.
So I thought a field was only a finite.
No, a field is always an integral domain. But a finite integral domain is a field.
But an integral domain is not always a field.
No, a finite integral domain is always a field. But an integral domain that is infinite is not necessarily a field. Z.
But a field is always an integral domain.
Yeah, exactly. Exactly. So we know how to prove these statements. So, and then if R is a finite commutative ring, then any non-zero element is either a unit or a zero divisor.
Can we do that by, like, you've done that a few different ways?
Yeah,
Can we
so
just do
I mean-
it if
I mean-
it is injected?
Yes. So in the notes, I corrected it in the recordings.
So it's better to do it if it is injected.
Yeah, so I will modify the statements because there is a mistake in that statement. But if I'm gonna ask you, I'm gonna ask you this statement. So I'll ask you if A is not a unit, I'll ask you the one that I did in the notes. So what I proved in the notes.
Oh. Like in
Don't worry.
class.
Yeah. Yeah, exactly. If A is not a unit, if A is not a zero divisor, then A is a unit. Is that how I did it? If A is not a zero divisor, then A is a unit. You could do the other way. Yeah, you could do the other way. But in class, I proved that if A is not a unit, then A is a zero divisor. That's how I proved it in class. Yeah, so these type of proofs you should expect. So in rings, you really have 5-6 proof from the first 4 lectures, right? No? 7. And the kernel is an ideal. Any ideal is the kernel. You have 7 proofs?
7.
7 to 9, okay. That's good. So you went through that.
I'll list it.
Oh, okay. Then the second part, the characteristic, you have maybe 10, 12 statements. I don't know how many, but they're all the same idea. It's the same idea. Did you memorize them?
There's a lot. But
Yes. That's the thing. That's what I want. If you know how to do them, then it should be clear. Okay. So please know these. The first 3 questions, it should just be like you in 15 to 20 minutes, assuring that you get 30 on 70 on this final. The first 15, 20 minutes.
In the first 20 minutes, we should get 30.
30, yeah, these are the proofs. These are the proof from the notes. It's 30 on 70.
One of the silos.
No, don't guess. Don't try to guess. Don't try to play that
No,
game and guess.
no. As in, that's one of the proofs.
No, I didn't say that. I didn't say. Did I say that one of the silos?
Yeah, you have said. You said silos second or third is going to be.
No, I didn't say that. I said I can ask.
Ordered. Cannot say
Yeah, you don't say that.
He said. Study it.
Okay, so
I said study it. Right? I mean, I didn't say it's going to be in. I said it's important. I said it's important because it's not. Maybe the proof is important, but the fact that the number of fixed points, if you have a P group, what is the theorem? Yeah, what is the theorem? If you have a P group acting on a finite G set, then the size of the set is congruent to the mod P. Yeah, maybe I want you to know that idea. Maybe I won't ask it, but I just want you to internalize that idea. You can forget. That's good. So if G is a finite P group and S is a G set, then the size of S is congruent to the number of fixed points mod P.
oh yeah. I wrote that one down. Wait a second.
You use it in Salo's theorem. You use it. It's not Silo, but this is the boom. This is the one that finished Silo's theorem. No, polynomials will just have calculations like this. So all the exercise I did today, except the one that are harder. For example, this a squared equal minus 1 business is fair. A squared plus a plus 1 is fair. Especially if I give you a hint, for example, if you have a squared plus a plus 1, and I ask you what would be the order of a, that makes it more simple, right? If I tell you to think in terms of groups. If I give you a hint, what would be the order of a if such a exists, for example?
But we would have to know the A.
I will give you. I can give you that.
Oh,
Yeah, I can give you that. Okay, so don't. I give hints in the finals. It's simple. Yeah, okay, but I mean, again, don't play that game of trying to guess what happened. If it's no, I mean, you can try. You can try. You can see what happens. Don't try to guess. Don't try to guess. Don't try to put your eggs in one basket.
I was just asking him if it's divisible by 4.